Thanks for inviting me here. Professor Lalit, Professor Yudhvir, Professor Preet, Professor Umesh Gupta. So thanks for inviting me. And I normally actually like to visit specifically colleges in Haryana. So, because the reason is I actually belong to Haryana. And I did my basically BTech from West College of Engineering Rohtak and then went to Delhi for my master and higher education. So the topic that was given to me, like when I discussed with Yudhvir, was supercomputing and supercomputers, right? So first of all, a fact, I don't work in supercomputing area. My area of research is data science, big data and AI. But of course for this talk, like I need to prepare, and it gave me a good opportunity to prepare and find out good facts which I should share with you guys, right? So first of all, how did we get first supercomputer in India? So how many of you know about that? First supercomputer that actually India had. So you should, yeah, you raise your hand. Param Sampuku, but how did we get it? So the reason for having our first supercomputer in India is that USA denied us access to the supercomputer. In 1987, we were actually asking them to give us a supercomputer named was Cray XP, right? And they denied us, telling us that if we use this supercomputer, if they give us this supercomputer, we are going to use it for nuclear warfare and all that, right? And citing that as a reason, they denied us. And that was the initiation of India working on supercomputing technology. And will you believe, within 4 years, we had our first supercomputer, and that supercomputer actually was Param 8000, right? And the speed of that supercomputer was as like your Cray XP. So this is actually first fact, right? And this supercomputer was made by CDAC Pune, okay, in 1991. Within 4 years, actually, we got this supercomputer, and it was made by CDAC Pune, right? So this is actually an interesting fact. The fact is that when we are denied access to some technology, then India has the capability to make its own technology, right? So this is actually is basically kind of a very good, I think, achievement that we should be feeling proud of, okay? Then you should also know that, see, all over the world, many countries actually are building their supercomputers, okay? India is also among these countries, but of course many other countries actually are building those supercomputers. But still actually you will see there is a kind of a ranking of these supercomputers. So the question comes, how do we do these rankings? Is there any particular way that you actually do this ranking? Because see, ultimately India can come up with its own ranking mechanism, USA can come up with its own ranking mechanism, and the other country can actually also come up with their own ranking mechanism. The issue is what? Issue is basically in a computer system there are so many parameters on which you can rank a supercomputer. You can rank a computer, let's say, right? You can rank a computer in terms of your latency. You can rank a computer in terms of, let us say, your energy consumption, right? You can rank a computer in terms of, let us say, throughput. So there are many parameters on which you can rank a computer, right? So how do we rank all these supercomputers in the world? So the way actually is basically using a set of benchmark, which are basically the standardized benchmark. So world has accepted those benchmarks for ranking supercomputer, and of course it should be transparent as well. It shouldn't be like I say, okay, fine, I ran this benchmark on my computer and I achieved this particular performance. That is not enough. I need to give the evidences, right? And the other countries should be able to reproduce those results. Then only that rank will be accepted. Fine. So there is a benchmark which was given by USA and Germany, right? There is a researcher in USA and there is a researcher in Germany, right? That 3 people actually who gave this benchmark, and till now, the time it was given till this point in time, that's the benchmark that actually is being used. And some of you, maybe from the mathematical background, right? So you will be happy to know that one of the benchmark problem is your linear programming problem. right? It's a LinPack solution, LinPack software. It's a dense matrix, and then you want to solve these variables, basically. You want to solve your variable linear equation, basically. You know, you have done that actually in your school time. But of course, the system problem is large enough to give you the challenge how fast you can compute it. Okay? Other than this linear programming, there are other problems like for energy, there are problems for graph processing, right? And some other dense data computation. So this is a kind of a collection of softwares that you need to run on your computer and then show your result. And where do you show your result? There are a couple of conferences which actually happen every year in the world. One of the conferences is supercomputing, right? Another conference actually is also in the same domain. And you need to show your records there. And then other people actually accept it. Then only we say, okay, fine, your results are good enough. And that's your rank. Fine. So even now, today, India's supercomputer is among top 100 supercomputers. And there was one time actually when we were actually 4th or 5th in terms of the ranking. So there was a computer which was developed by one subsidiary of Tata, which is Tata CRL, right? It's a computer which actually came from the industry, right? And it actually ranked at 4th supercomputer. Fine. So this is basically ranking. How do you do the ranking of supercomputers? And we should be feeling proud that we are still actually in top 100. This is actually a big achievement. But is it simply a technology race? Are we actually building these supercomputers only for the sake of coming in the top rank? It is not. There is a high utility of this particular technology, right? And that's why Government of India has spent crores of rupees. Even now, Government of India has a project of 10,000 crore rupees, which is National Supercomputing Mission, right? Where they want us to develop supercomputers and deploy them for different purposes, different usages, right? So if you just see the usages, right? What are the different usages actually which you can have from supercomputer? So one good application for supercomputing is weather modeling, weather forecasting, right? You will know that like maybe 15 years back, right? Professor Lilith will know, right? There used to be a DD news, right? Where you basically used to know, okay, fine, what will be the weather today or maybe in the week, right? But we were dependent on USA at that time. But now we actually have our own supercomputers doing this weather forecasting. And how again this weather forecasting is done? There is again a partial differential equation. The model actually is based on PDEs, mathematics again, right? Which actually is used to do the weather forecasting. And of course, in weather forecasting, if you just see the models, it is going to take Earth's surface, it is going to take your air, right? Your fluid velocity, right? Basically, modeling is going to be fluid modeling is going to be there, right? And many other actually systems actually which will be interacting with it. So you have a three-dimensional kind of a volume, right? The three-dimensional volume, then you have time, then you have your space, right? All of these dimensions make this particular problem of weather forecasting very, very complex. You have a lot of sensors using which you get the data, and then you need to basically churn out this data. You need to process this data, not one iteration, multiple iterations. You need to do the simulation, right? And then find out, okay, fine. After maybe thousands of iterations, you get a prediction. What I want to tell you is basically, first of all, this weather prediction is very compute intensive task, which actually requires a lot of data. And this kind of data processing is not possible without using these supercomputers. See, I come from the big data technology. So there is another paradigm of computing where you believe in using commodity machines. You have thousands of laptops or commodity machines which are talking to each other, and then you are doing your processing. But let me tell you, that kind of architecture, that kind of framework of big data technology wouldn't work for the problem like your weather forecasting. Because your problem is compute intensive. even for this partial differential equation, you have many systems which are interacting with each other. It's a tightly coupled problem, right? So that's why you need supercomputers. And the power of supercomputer is going to decide for how much duration you can do the forecasting, right? And how accurately you can do the forecasting. Okay? That actually should be clear to everybody. Why do we need supercomputers? So weather forecasting is one of the applications, right? But of course, there are other applications which are simulation-based applications. So what do you know by simulation? Why do we need simulations? So basically, simulation actually is going to be the alternative for doing the thing practically, right? So there are two alternatives. Either you do the thing practically, or you do simulations first and then find out, okay, which model actually or which policy is going to work. So if you do the things practically every time, it's going to be very cost intensive. Think about any surgery that you are doing on a human, right? And what actually you should do as a kind of a surgery. If you do the simulation first and then get confidence, or you get confident in yourself, oh, actually this is how I should operate this surgery, right? It is going to be the lesser chances of actually having some failures there. And believe me, the doctors, the surgeons actually who do critical surgeries, they spend hours and hours only to find out, only to see, okay, fine, how should I do this major or critical surgery, right? That's where actually the difference comes. And these simulations actually are cost-effective ways to know how do I do it. And the simulations actually are not only for the surgeries. There are many applications, even let's say scientific study, right? You want to study hydrogens or protons, right? There you have lot of data being generated and you want to basically process it from different aspects, different angles, right? Different viewpoint. And this is going to be possible only through simulation. Even a simple application of installing ATMs, let us say in a city. How many ATMs should I install at a particular location? It is going to ask you to do some simulation. Simulations of how many customers actually are going to reach on an ATM. What is going to basically know what is the average length of my queue on an ATM if I actually install only one ATM. What will happen if I actually have two ATMs? What will happen actually if there is a failure of an ATM? You have to see different aspects. And simulation actually is the way to find out final implementation that actually you want to do. Everybody with me till now, right? So what we have seen, okay, how did we get our first supercomputer? And there is a ranking mechanism. We also saw the usage of supercomputing, right, or supercomputers. Like, for example, we saw weather forecasting and then the simulations, scientific simulations. And even actually, you see the current warfare, as Professor Yudhvir was telling, right? This is basically asking us to use these supercomputing technologies again, right? Where if you, let's say, have a missile going towards the enemy side, right? You want to see, okay, fine, what will happen as with the actions of the enemy? Enemy can actually jam my communication of my missiles. If I am firing, let's say, thousands of missiles or thousands of drones, what is going to happen if they jam some of the drones? They can't communicate with each other. They can't communicate with the machine actually with which I am controlling that, right? Whether my target is changed, target position is changed, whether some of the drones actually has gone away. All of that actually need to be taken care of. Again, the simulation. And not only simulation actually. Simulation is one thing, but actually it's a real-time control. You want to process all of this sensor data of thousands of drones which actually you have sent to your enemy's side, right? And you want to control them in real time. You have to process this data in real time. So when you want to process this data in real time, basically you want to have a low latency. Low latency is the crux. Scalable computing is the crux, right? Low energy consumption is the crux. They are the parameters that actually you want to have when you are designing a supercomputer. Okay? So now, the question that actually I asked myself, so I have worked in big data technology, or I have used the laptops or desktop machines. How is a supercomputer different from a laptop? Right? So the first answer that I got was, okay, see, the supercomputer is basically 1 million times faster than your laptop. But how? What is the architectural difference of a supercomputer with a laptop? Right? So what I found that, first of all, in a supercomputer, as compared to your laptop, you have thousands of CPUs. It's basically kind of a cluster of mini nodes. It's again a cluster of mini nodes. And the focus is on fast computation, not on clock speed. So we have already got to the limit of our clock speed, how fast a processor can run. It is basically now cluster of processors, how can I use them effectively to do my computation as fast as possible. And there actually comes the metric which is called number of floating point operations. How many floating point operations I can do in a second. So currently, if you just see the fastest computer of USA, it basically processes, it can process around 1.2 exaflops operations in 1 second. So this exaflop is basically 10 power 18. And the fastest computer that India has around 540 petaflops, right? So basically, there's a huge gap. We are still in top 100, but actually we are still far away from there. So exaflops is basically not the clock speed, it is basically the number of operations that you can do per second. So this is actually one metric. Other thing that I see as an architectural difference, as I told you, like it's actually number of cores that you have, and each core actually can run multiple threads, multiple processing, right? It can do multi-processing, as like our single laptop. So you have actually kind of a hybrid kind of communication between the threads and the processes. When you talk about the threads communication with each other, it is going to be like I am running a process on a single computer, and there's a shared memory, and in the shared memory, these threads actually are communicating with each other. Okay? But once actually it comes to the communication of processes, this is going to be inter-process communication. So there are multiple interfaces. Let me tell you about, like, there is a message passing interface, there is a OpenMI interface, and there is a CUDA interface. You might have heard of GPUs now, right? Everybody actually is running AI workload and all that. So this kind of message passing or communication interface differentiate a supercomputer from a laptop. In laptop, normally the communication is going to be basically OpenMI, right? If you have CUDA also, now laptops actually have GPUs also, 1 or 2 GPUs, then you're going to have CUDA interface as well, or CUDA message passing interface as well. So you have millions of core in a supercomputer. Million is basically 10 lakh, right? So you have around 10 lakh, even more than that actually, as a number of cores in a supercomputer. Each of the core is going to have several GPUs, right? And then they actually are used to process your task where they would require the communication, and the communication is going to be through these different interfaces. Okay, you may not know the technical details, but actually you should know, okay, fine, there is going to be process-to-process communication, and a process will also have multiple threads which are going to communicate with each other, right? And CUDA is another way where I am delegating the task to some other devices, and they are basically doing the processing for me, and then I have a mechanism of communication between CPU and the GPU devices. So this is the processing part. But actually, what we see that in a supercomputer kind of technology, the bottleneck is not the computation. The bottleneck is basically this communication again. You need a interconnect so that these devices can communicate at a higher bandwidth. So we have, like, for example, bandwidth like InfiniBand, which is actually going to give you petabits, actually kind of petabits per second. That's a bandwidth that you have, right? And there actually the bottleneck. Believe me, even in big data technologies, bottleneck is not the cores or CPUs, right? Bottleneck is basically the communication. If you want to, let's say, transfer 1 gigabyte data, or maybe I should say 1 terabyte data now, the best way to send or transmit 1 terabyte data is basically store your data in a hard disk and then transmit this hard disk by courier, not by network. But network is going to be more costlier and more time-taking task. Okay, so this is basically kind of a supercomputing architecture where you have multiple cores, And GPUs, you have different message passing interface, shared memory versus non-shared memory. It is not like your CPU where you have uniform memory access. It is basically non-uniform memory access. And that is going to ask you to basically further optimize your processes or algorithms. Then comes your disk IOs. Disk IO is basically whenever you do any computation, you need to bring your data into main memory. But bringing the data from disk to main memory is again a costly operation. Again a difference of 1000 times, right? So can I do something to actually achieve better performance? And there comes the use of parallel distributed file systems, right? So these parallel file systems, basically all the CPUs and cores and GPUs actually are kind of talking to the disk, which is of petabytes, right? Where you are getting the data from into the main memory, and then you are doing your iterations. For example, all the AI models, like your natural language processing model, they actually, ChatGPT again, right? These kind of models which actually have billions of parameters which you need to tune so that they can generate accurate answers, right? They are going to ask you to, first of all, have a good computation, right? And of course, you want to do your convergence as fast as possible, where the role of machine learning algorithm will come. So even now, so we have like one of the, like 2020, actually there is a initiative again from Government of India, where Government of India wants to have a supercomputer where it is going to be used for having natural language processing models for Indian languages, right? It is going to have, of course, other tasks, whatever we want to have, but going to focus only on AI and ML. Actually, and this is being done by one of my good friend at IIT Bombay, Ganesh. He actually is the project leader of that particular problem, the task, right? And again, there are some IITs and IIITs fellows actually who are involved into that task, where you want to have a supercomputer specifically designed for AI ML kind of workload. Remember, what actually I'm trying to say, even these technologies like supercomputer is not like basically you make a supercomputer which will be used for all the tasks. No. You are basically kind of doing the customization for your particular task, right? So kind of computation that you require, how many disk IOs you require, how much communication you would require, can I do something at the algorithm level, should I need to do something at the architecture level? All of these questions need to be answered whenever you are customizing a particular technology to solve a problem. Okay, so we actually have now a supercomputer, as I told you, which is basically comes actually in top actually 100, right? As I told you, and 540 actually is the 540 petaflops. That's actually is the thing that actually we have. And the computer that I'm talking about, this is basically called Param Siddhi AI. The computer name is Param Siddhi AI, right? And there again, India is basically kind of taking initiative in terms of, first of all, this interconnect communication channel. How do we communicate, right? So there actually also the cores, the CPU architecture. So we are basically planning to have Rudra kind of architecture for the processing, right? And the Sanchar is the name of your communication channel, right? So these kind of initiatives are being taken. So I would say that there is one aspect where actually we got the technology when we were denied the access, and we actually did very well. Not only in terms of having the technology, but also using the same technology for solving tasks which actually are very relevant for us. Even for agriculture, it's actually multi-billion-dollar industry. You're doing weather forecasting, and that kind of thing actually can be used for your agriculture. Precision agriculture, what to actually sow, when to actually reap it, right? All of these decisions can be taken using supercomputing technology. Cyclone prediction actually is another thing, right? This can be done using supercomputers, right? Drones, defense, right? Many different applications that actually are possible with the use of supercomputer, and we should be actually feeling happy and should be feeling proud that actually India has its own technology, right? So with this, I would like to conclude. Until unless you have specific questions, I will be happy to answer those questions. Thank you.